Hey guys, so today we're going to be talking about areas between curves and volumes of revolution. The first question is the old classic problem that asks us to divide an area enclosed by two curves into two equal parts using a line y equals k. And always the first step when solving this kind of problem is to draw out your equations on a graph. I've done this on Desmos, and it's pretty convenient right here, you got it. You want to do this on your test every time. So this is going to be our line y equals k, this is our line y equals 4, and this is our function y equals x squared. The line y equals k is dividing y equals x squared into two regions, our green one and our orange one, that have equal areas. So our task is to find out what that value here equals in order to do that. And to do that, we're going to use integration. But first, we want to convert into x equals for this equation because integrating with respect to y instead of x is going to be easier here since we're given y values for our k and for our upper equation of y equals 4. So to do this, we're just going to set y equals x squared and take the square root of both sides, and we simply get x equals plus or minus the square root of y. And this is the x equals plus the square root of y, this is x equals minus the square root of y, and those combined, x equals plus or minus the square root of y, is equivalent to y equals x squared, just in different terms of variables, which is going to make it easier for us in a moment. So what we want to do now is we want to take a look at this and say, okay, we need to figure out an expression that gives us the area under this curve, and it's going to have to cover not only this area right here, but both these two. So right now we've got the positive y equals squared, x equals square root of y, and the negative. We want to combine those two by using our area formula right minus left, right? So we're going to take the square root of y minus the negative square root of y equals the integral of 2 square roots of y dy, which is the whole thing. So this basically will give us, whenever we plug in some bounds, the area of y equals x squared just with respect to y. We're going to use this now to actually find y equals k. So what we're going to do is we're going to integrate from 0 to k, y equals 0 to y equals k, of this function, dy, and that green area that we just got is going to be equal to the orange area, which is going to be the integral from k to 4 of 2 square roots of y dy, which is right here. What we're going to do here is just cancel the 2's and use fractional exponents instead of radicals because that makes our lives much easier when integrating. And now we're just going to use the power rule of integration right here. Now all we've got to do is cancel the 2/3, no need for those anymore, and use the fundamental theorem of calculus to evaluate the integral. So we're just going to plug in our bounds. So we get k to the 3/2 equals 4 to the 3/2 minus k to the 3/2. Add k to the 3/2 to both sides, and we get 2k to the 3/2 equals, and then just simplify 4 to the 3/2 to 8, which is basically 4 cubed is 64. Square root of 64 is 8. That's how you get that. And then divide by 2 and get k to the 3/2 equals 4. Now all you got to do is take 4 to the 2/3 power, which ends up being the cube root of 16, which equals 2 cube roots of 2. And the answer is not that bad. So now we're switching gears a little bit. We were just talking about area between curves. Now we're switching to volume of a solid generated by revolving around the x-axis. Again, with these problems, you just want to draw it out. I've done that right here. So it's asking us to revolve it around the x-axis, kind of like this. These are our two functions, y equals x squared, just like the last problem, and y equals the square root of x. And we're only dealing in the first quadrant, so we don't really care about these sections, just this. Now the first thing we want to do here, after we've drawn the curves, is determine where these intersect, because I've got it conveniently drawn on Desmos right here, and you can tell that it's just 1, 1, right? But on your test, it might not be that easy. So what you want to do is set these two equal to each other, square both sides to get x to the 4th equals x, subtract by x, and then you can just factor x times the quantity x cubed minus 1 equals 0. And then your two solutions are obviously x equals 1 and x equals 0. we already know about x equals 0, but this gives us our intersection point right here. And if we want to know the y value for some reason, we just plug that into either of these since they both give the same value since they're intersecting at that point. So now what we want to do is we want to use our volume formula when revolving around the x-axis, or really any line. So that is the volume equals pi times the integral from a to b of our outer radius, g of x squared, minus our inner radius, f of x squared, all dx. To determine what our outer radius is, we just look at which one is farther away from the x-axis. And in this case, it's the y equals the square root of x. And our inner radius, which is this guy right here, is y equals x squared. So all we're going to do is just plug in our bounds and plug in our equations. And we've got that right here. And from now on, it's just simplifying. We get volume equals pi times the integral from 0 to 1 of x minus x to the fourth dx. Use power rule once again. Volume equals pi times the integral of x squared over 2 minus x to the fifth over 5, evaluated from 0 to 1. Now we're just going to use fundamental theorem of calculus again, and we get volume equals pi times the quantity 1/2 minus 1/5, and all you got to do is find the common denominator, which is 10. So we get 5 pi over 10 minus 2 pi over 10 equals 3 pi over 10, and now we're done. That's it. That's the volume. This problem right here is a little bit different because instead of revolving around the x-axis, we're revolving around the specified line, which in this case is y equals 10. Again, we're going to draw it. So you might be intimidated by all these lines and all these equations right here, but really it's pretty simple. It's just like our last problem. These two are just telling us our bounds, x equals 1 and x equals 8. We're just integrating within this region. About the line y equals 10, normally if we're revolving around the x-axis, this would be y equals 0, but it's just a different y value this time, right? It's just y equals 10, so it's really not that bad. And we've got our function, y equals the cube root of x, and another easy function, which is y equals 3. So right here, we want to start thinking about how are we going to actually find the area of this thing and revolve it around the line y equals 10 like this. Well, it helps to start drawing some lines so that we can determine our inner and outer radius, right? Because we're using the same formula as we were before, the outer minus the inner squared, whatever. But we just got to figure out what those are. So let's do that by drawing this line. So this is going to be our inner radius, right, our f of x, because it is closest to y equals 10. And all it is the value of 10 minus the value of 3, because that's the line right here, y equals 3. And then you just get this constant inner radius. The outer radius is a little different because it's changing depending on where you are in this region, but it's the same principle. It's just your value of 10, which is this whole region right here, from right here to right here, minus your function value, which can be like right here to right here or right here to right here, depending on where your x is. And that is just represented the same way as we do like 10 minus 3. It's just 10 minus the cube root of x. So we're just going to plug that in right here. These correspond. So pi times the integral from 1 to 8, which are our bounds, 1 to 8, of 10 minus the cube root of x squared. It's our outer radius, 10 minus the cube root of x, minus 10 minus 3 squared, which is just 10 minus 3. So from now on, once again, it's just simplifying. We're going to do a little bit of foiling, and this is just 7, so it becomes 49. We get volume equals pi times the integral from 1 to 8 of 100 minus 20 cube roots of x plus the cube root of x squared minus 49 dx. So we're just going to combine these two terms. Volume equals pi times the integral from 1 to 8 of 51 minus, and now we're going to use our fractional exponents again, 20x to the 1/3 plus x to the 2/3 dx. And finally, we use power rule once again for integration. And it gets kind of messy, so this is going to take us a little bit longer, but this becomes 15. So now let's just plug in our bounds, use the fundamental theorem of calculus. Pi times the quantity 51 times 8 minus 15 times 8 to the 4/3 minus 35 times 8 to the 5/3 minus 51 plus 15 minus 3/5. It's a mouthful. We're just going to multiply these two out, get 408. This 8 to the 4/3 simplifies to 16 because 2 cubed to the 4/3 becomes 2 to the 4th, which becomes 16. Minus 3/5, same concept here, becomes 32. And then minus, we're going to combine these two. Negative 51 plus 15 equals negative 36, and minus 3/5. And more simplifying, we multiply these two out, we get 240. If we multiply 3 times 32, we get 96, and then we're going to combine that fraction with the negative 3/5 to get 96 minus 3 all over 5. We're going to keep the negative 36 right here. Now we just combine all these three constant terms and we simplify the fraction, and we get pi times the quantity 132 plus 93 over 5. And finally, we just find the common denominator. Volume equals pi times the quantity 660 plus 93 over 5, and we get our final answer of 753 pi over 5.